Part 1. Introduction to Ice Giants. What sets Uranus and Neptune apart? In the dark, distant reaches of our solar system, far beyond the orbit of Saturn, lie two cold, mysterious worlds. They are not as massive as Jupiter, nor as radiant as Saturn, but they are every bit as intriguing. Uranus and Neptune. These are the ice giants, the farthest known major planets from the Sun. They are colder, stranger, and more elusive than their gas giant cousins, and for decades they have quietly defied expectations. What makes them different? Why do they matter? And what secrets do they still hold in their icy blue depths? The term ice giant might be a little misleading at first. After all, Uranus and Neptune are not made of frozen water or giant glaciers. Instead, the name comes from their internal composition. Unlike Jupiter and Saturn, which are composed mostly of hydrogen and helium, Uranus and Neptune contain a much higher proportion of heavier elements, what astronomers often call ices, such as water, ammonia, and methane. These materials are in slushy or compressed fluid form deep inside the planets, but the label has stuck. The result is a new category of planet, not gas giants, not rocky terrestrials, but something in between, ice giants. At first glance, Uranus and Neptune appear similar. They're nearly the same size, with Uranus only slightly larger in diameter and Neptune slightly more massive. They both have bluish hues. Uranus a pale turquoise, Neptune a deep sapphire blue. They have similar atmospheric compositions, thick with hydrogen, helium, and a dash of methane, which absorbs red light and gives them their distinctive colors. Both are surrounded by systems of faint rings and numerous moons. But despite their outward similarities, Uranus and Neptune are fundamentally different in some surprising ways. Let's start with their positions. Uranus orbits the Sun at about 2.9 billion kilometers, roughly 19 times farther than Earth. Neptune is even farther out, about 4.5 billion kilometers away, or 30 times Earth's distance from the Sun. At these distances, sunlight is feeble. On Neptune, the Sun appears as just a bright star, not much more than a point of light in the sky. Temperatures are frigid. And yet, Neptune, strangely, emits more internal heat than Uranus. In fact, Neptune radiates about 2.6 times more energy than it receives from the Sun. Uranus, by contrast, barely gives off any excess heat at all. This puzzling difference suggests that something happened to Uranus, a dramatic event early in its history that may have stripped away or redistributed its internal heat. One leading theory is that Uranus suffered a colossal collision with a massive protoplanet, knocking it sideways and disturbing its internal structure. Today, Uranus spins on its side, tilted over by about 98 degrees. Its axis lies nearly in the plane of its orbit, meaning it essentially rolls around the Sun like a barrel. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. No other planet behaves this way. Neptune, on the other hand, rotates more upright with an axial tilt of about 28 degrees, similar to Earth's. Its dynamic atmosphere is home to some of the fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour. These winds drive massive storm systems, including dark spots similar to Jupiter's Great Red Spot. Voyager 2, the only spacecraft ever to visit Neptune, spotted one such storm in 1989, the Great Dark Spot, but it later vanished, and others have appeared since. Neptune, it seems, is a planet in motion. That brings us to the only mission that has ever flown past the ice giants, Voyager 2. Launched in 1977, it reached Uranus in 1986 and Neptune in 1989, giving us our first and only close-up images of these distant worlds. Voyager 2 revealed Uranus's faint rings, its strange magnetic field, and its icy moons, including the fractured and mysterious Miranda. At Neptune, it found geysers erupting on the moon Triton, clouds streaking across the planet's atmosphere, and evidence of an internal heat source. But both encounters were brief, mere days of observation after a journey of nearly a decade. Since then, the ice giants have remained largely unexplored. Why haven't we returned? Part of the reason is distance. A round-trip mission to Neptune or Uranus requires a long time, immense fuel, and careful planning. Most spacecraft launched so far have focused on nearer or larger targets. But now, with growing interest in the outer solar system and advancements in propulsion and instrumentation, new missions are being proposed. Missions that could finally unveil the long-hidden secrets of these enigmatic planets. One reason scientists are so eager to return is that Uranus and Neptune may hold clues to how planets form. They are thought to have originated in a region of the early solar system, rich in ices and dust, materials that didn't survive as well closer to the Sun. By studying their composition and internal structure, we can learn more about the building blocks that formed not just our own planets, but planets orbiting other stars as well. In fact, exoplanet discoveries have shown that ice giant-like worlds may be among the most common types of planets in the galaxy. Many exoplanets we've detected so far are similar in size and mass to Uranus and Neptune. They don't have solid surfaces, but they aren't as massive or hot as Jupiter-like gas giants either. If we want to understand what those distant worlds are like, we need to understand our own ice giants first. Uranus and Neptune also challenge our models of planetary magnetism. Both planets have strange, lopsided magnetic fields, not centered on the core, but offset and tilted at odd angles. This suggests that their magnetic fields are generated in unusual regions of their interiors, perhaps in a shell of conducting fluids rather than deep in the core. Studying how these fields behave can tell us a lot about the physics of planetary dynamos, the same kind of magnetic processes that protect Earth from cosmic radiation. Their atmospheres are also chemically rich. While they share the same basic ingredients as Jupiter and Saturn, they appear to have more methane and perhaps more water and ammonia deeper down. These differences could explain why their clouds and colors appear the way they do. But many questions remain. Why is Neptune darker than Uranus, despite their similar methane content? What causes the high-speed winds and dynamic weather on Neptune? And why is Uranus so relatively featureless in visible light? The moons of Uranus and Neptune also hold fascinating mysteries. From Miranda's broken terrain to Triton's geysers and retrograde orbit, these satellites are more than just frozen rocks. They are clues, records of ancient collisions, captured bodies, and internal activity. Some may even harbor subsurface oceans, like Europa or Enceladus, raising the tantalizing question of whether life could exist that far from the Sun. And then there are the rings. Both Uranus and Neptune have ring systems, but they are faint, dark, and narrow, very different from Saturn's. Uranus's rings were discovered from Earth in the 1970s, while Neptune's were only revealed by Voyager. They are composed of dark material, possibly organic compounds or radiation-darkened ice. Unlike Saturn's broad, bright rings, these are barely visible, and their origins remain a mystery. Were they formed from shattered moons? Are they the remnants of captured debris? Understanding these rings could help us reconstruct the violent history of the outer solar system. So what truly sets the ice giants apart? It's not just their distance or their color or their size. It's their identity as a unique class of planet, one that bridges the gap between gas giants and terrestrial worlds. They are cold, tilted, windy, and magnetic. They are quiet giants, often overlooked, yet filled with potential. As we look to the future, missions are being planned to return to these worlds. NASA has considered a Uranus orbiter and probe mission, and the scientific community has repeatedly ranked it as a top priority. Such a mission could enter orbit, deploy atmospheric probes, and conduct long-term observations of Uranus and its moons. Similar proposals exist for Neptune, especially to revisit Triton and its geysers. These missions are not just about filling gaps in our knowledge. They are about exploring the unknown and asking the kinds of questions only the universe can answer. In this lecture, we've laid the foundation for our journey into the ice giants. We've seen how Uranus and Neptune defy expectations, how they differ from each other and from the gas giants, and how they hold clues to both the past and the future of planetary science. In the lectures to come, we'll look more closely at each planet, beginning with Uranus, the tilted giant, whose seasons last decades and whose moons circle a world on its side. The ice giants are waiting. And now, we begin our descent into their cold and fascinating depths. Part 2. Uranus, the tilted giant. Among all the planets in our solar system, Uranus stands out for one remarkable reason. It spins on its side. While Earth and the other planets rotate more or less upright, tilted only slightly as they orbit the Sun, Uranus is tipped over by a staggering 98 degrees. It's as if someone knocked the planet over in its youth, and it never stood up again. This extreme tilt defines everything about Uranus: its seasons, its weather, its magnetism, and the orbits of its moons. In this lecture, we're diving into the strange, sideways world of Uranus to explore what makes this ice giant so unique and so intriguing. Let's begin with the basics. Uranus is the seventh planet from the Sun, orbiting at a distance of about 2.9 billion kilometers. It's the third largest planet in the solar system by diameter and fourth largest by mass. It's made primarily of hydrogen and helium, but with a much larger proportion of water, methane, and ammonia, materials that form icy and slushy layers deep inside. These ices are not frozen in the way we think of ice on Earth. They exist under immense pressure and in exotic fluid forms that we're still learning how to describe. When we look at Uranus from afar, what we see is a calm, pale blue orb. Its color comes from methane in the upper atmosphere, which absorbs red light and reflects blue. Compared to the dramatic stripes of Jupiter or the ringed splendor of Saturn, Uranus appears almost featureless. For many years, astronomers thought it was a quiet, inactive world. But as we'll see, that calm face hides some very curious activity. First, let's talk about that tilt. No other planet has an axial tilt anywhere close to Uranus's. This means that its poles point almost directly at the Sun during parts of its 84-year orbit. One pole experiences a continuous summer of sunlight for about 42 years, while the other sits in long darkness. Then, half an orbit later, they swap. The equator, which on Earth and other planets receives the most direct sunlight, gets relatively little on Uranus. This tilt has strange effects on the planet's weather and seasons. For most of its orbit, sunlight falls unevenly on different parts of the planet, and yet Uranus's atmosphere seems surprisingly bland. Unlike Neptune's swirling storms or Jupiter's raging Great Red Spot, Uranus appears to have little visible weather. But this perception began to change after the year 2000, when more detailed telescopic observations, especially from the Hubble Space Telescope and ground-based observatories, began to reveal faint cloud bands, bright storms, and shifting atmospheric features. Uranus may be quieter than its cousins, but it is not completely still. In fact, seasonal changes do occur on Uranus, but they happen slowly. When the sun begins to rise on one pole after decades of darkness, the atmosphere starts to shift. Winds pick up, storms can form, and cloud patterns change. Because Uranus takes 84 Earth years to complete one orbit, each season lasts about 21 years. We've only been watching Uranus through modern telescopes for a short fraction of that cycle, so we may still be in the early stages of understanding its atmospheric rhythms. Another mystery is Uranus's internal heat, or rather, its lack of it. Most of the giant planets emit more heat than they receive from the sun. This internal heat comes from the energy left over from their formation, and from the slow compression of their massive atmospheres. But Uranus is different. It radiates almost no extra heat at all. It's nearly in balance with the sunlight it absorbs, which is unusual for a planet of its size. Why is Uranus so cold? One possibility is that it lost its internal heat long ago, perhaps because of that ancient collision that tipped it over. Such a violent impact could have disrupted the internal layers, shutting down the processes that normally release heat. Or maybe the heat is still there, but trapped beneath layers of material that act like insulation. Whatever the reason, Uranus holds the title of coldest planet in the solar system, with temperatures dropping below -220 degrees Celsius. Then there's the magnetic field, another area where Uranus breaks the mold. Most planets, like Earth and Jupiter, have magnetic fields that are roughly aligned with their rotation axes. But Uranus's magnetic field is wildly tilted, about 60 degrees off from its axis, and it's not centered at the core. Instead, it's lopsided, offset by almost a third of the planet's radius. This gives Uranus a magnetosphere that's twisted and asymmetric, changing shape dramatically as the planet rotates. The magnetic field likely originates in a layer of electrically conducting fluid, possibly a form of ionized water or ammonia, surrounding a small rocky core. Uranus also has rings. They're not as prominent or beautiful as Saturn's, but they're fascinating in their own right. Discovered in 1977, Uranus's rings are dark, narrow, and made mostly of small particles, possibly covered with radiation-darkened organics. There are at least 13 known rings, with the brightest and densest being the Epsilon ring. These rings are maintained by the gravity of small nearby moons, which help keep them from dispersing. Unlike Saturn's bright icy rings, Uranus's are difficult to see without powerful telescopes, but they're an essential part of the planet's identity. Speaking of moons, Uranus has 27 known natural satellites, all named after characters from the works of William Shakespeare and Alexander Pope. The largest are Titania, Oberon, Umbriel, Ariel, and Miranda. These moons orbit Uranus in its equatorial plane, which, due to the planet's tilt, means they move almost vertically relative to the rest of the solar system. It's as if the entire moon system was turned on its side. Miranda, in particular, is one of the most geologically bizarre objects we've ever seen. When Voyager 2 flew by in 1986, it revealed a surface of cliffs, canyons, and jumbled terrain that looks like pieces of different worlds stitched together. Some scientists believe Miranda may have been shattered by an ancient impact and reassembled under gravity. Others think its strange features are the result of internal heating and resurfacing. The mystery remains unsolved. Uranus's other large moons are equally fascinating. Ariel has signs of tectonic activity and smooth plains that may have been resurfaced by icy lava. Umbriel is darker and more heavily cratered, while Titania and Oberon are larger and may have retained subsurface oceans in their past. Recent studies suggest that at least some of Uranus's moons could still harbor liquid water beneath their icy crusts, making them intriguing candidates for future exploration. Despite all its oddities, Uranus has been visited only once by a single spacecraft. Voyager 2's flyby in 1986 lasted just a few days, and the data it collected remains our primary source of information. In the decades since, Uranus has been largely forgotten by mission planners, but that may soon change. NASA and other space agencies are now seriously considering new missions to the ice giants. The Uranus Orbiter and Probe concept, which has been ranked as a top scientific priority, would send a spacecraft into orbit around the planet, accompanied by a probe to dive into the atmosphere. Such a mission could study the planet's weather, magnetosphere, rings, and moons in detail over several years. Why does this matter? Because Uranus is more than just an oddball. It's a representative of a class of planet that seems to be common in our galaxy. Many of the exoplanets we've discovered so far are similar in size and mass to Uranus. By studying it up close, we can better understand not just our own solar system, but the architecture of planetary systems throughout the universe. Uranus challenges our assumptions. It reminds us that planets can be tipped over, frozen, dim, and still completely fascinating. It invites us to look beyond the obvious and to question what we think we know about how planets form, evolve, and behave. As we leave the world of Uranus behind, we journey onward to its sibling, Neptune, a planet with deep blue storms, fierce winds, and a moon that may have been captured from the distant Kuiper Belt. The story of the ice giants is only just beginning, and the next chapter promises even more surprises. Part 3. Neptune, the dynamic blue world. Neptune, the eighth and most distant planet in our solar system, is a world of extremes. Though it lies far beyond the warmth of the sun, Neptune is a place of turbulent weather, supersonic winds, and dramatic atmospheric activity. It's colder than any place on Earth could ever be, yet it pulses with internal heat and energy. With its deep blue hue, mysterious storms, and orbiting moons and rings, Neptune challenges our assumptions about the outer solar system. In this lecture, we journey to this distant ice giant to understand what makes Neptune so dynamic, so beautiful, and so unexpectedly powerful. Discovered in 1846, Neptune was the first planet located not by direct observation, but through mathematics. Astronomers had noticed that Uranus wasn't following its predicted path across the sky. They suspected another planet's gravity was pulling on it. Using calculations alone, they pinpointed the location of Neptune, and when telescopes were aimed at that spot, there it was. It was a triumph of science and a turning point in our understanding of the solar system. Neptune is about 4.5 billion kilometers from the Sun, 30 times farther than Earth. At that distance, sunlight is incredibly faint, and yet Neptune is one of the most vibrant-looking planets in the sky. Its brilliant blue color comes from methane gas in its upper atmosphere, which absorbs red light and reflects blue. But methane alone doesn't fully explain the intensity of the color. There may be unknown elements or processes that give Neptune its signature deep azure glow. In terms of structure, Neptune is quite similar to Uranus. Both are classified as ice giants, with interiors composed of water, ammonia, and methane ices and slushes, rather than the mostly hydrogen and helium makeup of Jupiter and Saturn. Neptune has a small rocky core, surrounded by a mantle of icy materials, topped by a thick atmosphere. Its density is higher than Uranus's, and it's slightly smaller in size, but more massive, making it the densest of the four giant planets. Despite its distance and freezing temperatures, Neptune is anything but quiet. Its atmosphere is a dynamic cauldron of motion. Winds roar through its upper layers at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound, and the fastest sustained winds on any planet in the solar system. These winds drive the formation of massive storm systems and dark spots, vortices that appear and vanish over time. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit the planet, it captured an enormous storm in the southern hemisphere, known as the Great Dark Spot. It was similar in size and shape to Jupiter's Great Red Spot, with wind patterns swirling around its edges. But unlike Jupiter's centuries-old storm, Neptune's dark spot disappeared a few years later, and new ones have formed since. This tells us that Neptune's atmosphere is incredibly active and constantly changing, with storms that may form and dissipate on much shorter timescales. Another curious feature captured by Voyager was a fast-moving white cloud nicknamed Scooter. This high-altitude cloud zipped around the planet in just a few hours and gave scientists insight into the complexity of Neptune's weather layers. Observations since then have shown more cloud activity, particularly near the equator and poles, further confirming that Neptune is far from static. One of the great mysteries of Neptune is its internal heat. Like Jupiter and Saturn, Neptune emits more energy than it receives from the Sun, about 2.6 times as much. This is especially striking because its sister planet Uranus, which is structurally similar, barely emits any internal heat. Scientists aren't entirely sure why Neptune is still so warm inside. It may be due to the way heat is transported through its atmosphere, or differences in its formation history. Whatever the cause, this internal energy fuels Neptune's violent weather and contributes to its overall dynamism. Neptune also has a magnetic field, but like Uranus, it's unusual. It is not aligned with the planet's rotation axis and is offset from the planet's center. This suggests the magnetic field is generated not deep in the core, but in a shell of conductive fluid closer to the surface. The result is a complex shifting magnetosphere that rotates every 16 hours and creates intense auroras near the poles, though they're much fainter than those on Earth or Jupiter due to the low levels of incoming solar energy. Orbiting Neptune is a system of rings and moons. The rings were first confirmed in 1989 during Voyager 2's flyby, although hints of them had been seen from Earth. They are faint, dark, and narrow, much less prominent than Saturn's. The rings are made of small dust particles and possibly radiation-darkened ices. One of the oddest features is the presence of ring arcs, bright clumps that seem to defy the laws of physics by not spreading out evenly. These arcs may be stabilized by gravitational interactions with nearby moons, particularly Galatea. Speaking of moons, Neptune has at least 14, and the most significant by far is Triton. Triton is one of the most unusual and intriguing moons in the solar system. It's the only large moon that orbits its planet in the opposite direction of the planet's rotation, a retrograde orbit. This strongly suggests that Triton did not form around Neptune, but was captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. The capture of such a large object would have disrupted Neptune's original moon system and possibly led to collisions or ejections. Triton is roughly the same size as Pluto and shares many characteristics with it. Its surface is icy and reflective, with nitrogen frost and strange cantaloupe-like textures. When Voyager 2 passed by, it observed active geysers spewing dark material into space, proof that Triton, despite its distance from the Sun, is still geologically active. Beneath its frozen shell, Triton may have a subsurface ocean kept warm by tidal heating caused by Neptune's gravity. If so, Triton becomes yet another world, like Europa and Enceladus, that could potentially harbor the ingredients for life. The other moons of Neptune are mostly small and irregular, likely captured asteroids or remnants of past collisions. Among them is Nereid, which has one of the most eccentric orbits of any moon in the solar system. There's also Proteus, one of the largest inner moons, which is oddly shaped and heavily cratered. Many of these moons remain mysterious due to limited observations. Neptune's great distance makes it difficult to study, but modern telescopes, especially the Hubble Space Telescope and ground-based observatories with adaptive optics, have provided occasional glimpses of its changing atmosphere and cloud formations. However, there is only so much we can learn from afar. A dedicated mission to Neptune could answer many of the questions that have puzzled scientists since Voyager's brief encounter over 3 decades ago. So what's next for Neptune? Several mission concepts have been proposed. One is a Neptune orbiter with a Triton lander or atmospheric probe. This mission would spend years orbiting the planet, mapping its atmosphere, rings, magnetic field, and moons, and conducting flybys of Triton to explore its surface and subsurface. Another idea is a flyby mission that could reach Neptune more quickly, offering new insights and high-resolution imagery. While these missions are still on the drawing board, growing interest in outer solar system science makes them increasingly likely in the coming decades. Neptune is more than a distant blue dot. It is a world of storms and silence, of hidden oceans and mysterious heat. It challenges our understanding of what a cold, distant planet should be. It spins with energy, defies expectations, and whispers secrets we've only just begun to hear. As we turn our attention to Neptune's family of moons, we'll see how its most intriguing satellite, Triton, holds clues to the early history of the solar system, and perhaps even to the possibility of life beyond Earth. The story of the ice giants isn't finished. It's just getting colder, darker, and more fascinating. Part 4. The Moons of Uranus. Tilted Orbits and Hidden Mysteries? When Voyager 2 flew past Uranus in 1986, it gave humanity its first close look at a planet unlike any other, tipped sideways, pale blue, and faintly ringed. But what it also revealed, in glimpses and flybys, was that Uranus's moons are just as strange as the planet they orbit. They don't just go around Uranus, they orbit in lockstep with its unusual tilt, following its equator like dancers around a spinning barrel. These moons, many named after characters from Shakespeare and Alexander Pope, are icy, scarred, fractured, and possibly hiding oceans deep within. In this lecture, we dive into the little-known world of Uranus's moons, a family of frozen satellites orbiting sideways in one of the solar system's most mysterious planetary systems. Uranus has at least 27 known moons, a mix of large and small bodies, inner ring shepherds, and distant irregular satellites. These moons can be divided into 3 groups. The inner moons, which are small and orbit close to the planet. The 5 major moons, which are the largest and most geologically interesting. And the outer irregular moons, likely captured objects with distant, tilted orbits. But before we meet the moons individually, let's look at how they behave. Because Uranus's axis is tilted by 98 degrees, its equator lies almost perpendicular to its orbit around the Sun. That means the moons, which orbit along the equatorial plane, move in nearly vertical paths relative to the rest of the solar system. It's as if the entire moon system has been tipped sideways. From Earth, the orbits appear as long, looping arcs, giving the system a bizarre, almost alien geometry. The 5 largest moons of Uranus are Miranda, Ariel, Umbriel, Titania, and Oberon. Each one is a world of its own, about halfway between an asteroid and a dwarf planet in size. These moons are composed mainly of water, ice, and rock, with surfaces scarred by impact craters, fault lines, and ridges. But what makes them compelling is that several of them show signs of geological activity, evidence that they may have once had, or may still have, internal oceans. Miranda is the smallest and perhaps the most fascinating. It's only about 470 kilometers in diameter, yet its surface looks like it's been shattered and reassembled. When Voyager flew past, it revealed a chaotic landscape of deep canyons, giant fault scarps, and patchwork terrain. One feature, Verona Rupes, is a cliff that may be as much as 20 kilometers high, making it the tallest known cliff in the solar system. Some scientists speculate that Miranda was once broken apart by an ancient impact and reformed under gravity. Others think its strange terrain may be the result of tidal heating, pulling and stretching the moon's interior and resurfacing it in patches. Next in line is Ariel, a relatively bright and young-looking moon, geologically speaking. Ariel's surface shows signs of tectonic activity, with long valleys and ridges stretching for hundreds of kilometers. Some of its canyons may have been formed by cryovolcanism, ice volcanism, where icy materials float up from beneath the surface. These features suggest that Ariel experienced a period of internal heating and resurfacing, possibly caused by tidal interactions with Uranus or neighboring moons. Umbriel, in contrast, is dark and heavily cratered, showing fewer signs of recent activity. It has a strange bluish ring around one large crater and a generally older surface. Its lack of resurfacing suggests that Umbriel has been geologically quiet for a very long time. But its interior composition, like the others, remains largely unknown. Titania is the largest of Uranus's moons, about 1,600 kilometers in diameter. It shows long fault systems and deep canyons, indicating some internal activity in the past. Its surface is a mix of cratered highlands and smooth plains, hinting at past eruptions of icy material. Oberon, the second largest moon, is darker and older looking, with large impact craters and bright ejecta rays. It also has some unusual surface features, including ridges that may point to internal processes that once shaped the crust. What ties these moons together is their composition and the possibility of subsurface oceans. Recent studies, including observations from Earth-based telescopes and reanalysis of Voyager data, suggest that some of Uranus's major moons may have enough internal heat, possibly generated by radioactive decay or tidal flexing, to maintain liquid water beneath their icy shells. If true, that places them in the growing list of ocean worlds in the solar system, alongside Europa, Enceladus, and Triton. These subsurface oceans would be incredibly difficult to detect from afar, but their existence would raise exciting questions. Could there be hydrothermal vents at the base of these oceans? Could life exist in such hidden, dark, and isolated environments? The presence of even the ingredients for life, water, energy, and organic molecules, would make Uranus's moons vital targets for future exploration. Closer to Uranus are the inner moons, small, irregularly shaped bodies that orbit within or near the planet's ring system. Names like Puck, Portia, Cressida, and Juliet belong to this inner family. These moons are mostly composed of water ice, have low reflectivity, and are probably ancient, battered remnants of a past era. They are gravitationally tied to the planet's rings, shaping and stabilizing them through their motions. Farther out are the irregular moons, such as Sycorax and Caliban, which have distant, inclined orbits. These moons are likely captured objects, similar to many of Jupiter's outermost satellites. Their orbits suggest a history of gravitational disruption and perhaps collisions in the early solar system. They're too small and too far to be studied in detail right now, but they complete the picture of Uranus's moon system as diverse, complex, and dynamically rich. And yet, for all their variety, Uranus's moons remain largely unexplored. We have no high-resolution images of most of them beyond the few Voyager 2 captured in 1986. In fact, much of what we know comes from brief flybys, telescope observations, and computer modeling. The rest is a mystery, waiting for the right mission to reveal it. That mission may soon come. The proposed Uranus orbiter and probe, currently prioritized by NASA's Decadal Survey, would carry instruments to study the planet, its atmosphere, rings, and moons. Over several years in orbit, it could conduct close flybys of the major moons, map their surfaces, search for magnetic fields or internal oceans, and study their geology in unprecedented detail. It could also deploy a probe into Uranus's atmosphere to finally learn what lies beneath its pale blue clouds. The moons of Uranus don't have the fame of Jupiter's Galilean satellites or Saturn's Enceladus and Titan, but they may be just as important. Their fractured surfaces and hidden oceans are like frozen pages in the history book of the solar system. They carry clues about the birth of icy worlds, the dynamics of tilted planetary systems, and the conditions that might support life in the most unexpected places. As we prepare to move outward to Neptune's domain, we'll find another family of moons, smaller in number, but home to one of the most fascinating satellites in the solar system. Triton, Neptune's retrograde companion, is more than just a captured object. It is a geologically active world that may harbor a subsurface ocean and may once have been a dwarf planet in its own right. In our next lecture, we'll explore the moons of Neptune, fewer in number but rich in mystery and history. Part 5. The Moons of Neptune, Triton and the Captured Worlds. Neptune, the distant blue giant of our solar system, is not alone. Orbiting it is a diverse collection of moons, each with its own story, shape, and path. But one of them stands apart: Triton. It's not just Neptune's largest moon. It's one of the strangest and most scientifically intriguing bodies in the entire solar system. It spins the wrong way, erupts icy geysers into space, and may conceal a liquid ocean beneath its frozen shell. Triton is a captured world, a former wanderer now locked in orbit around Neptune. In this lecture, we explore Neptune's moon system, with a special focus on Triton, the icy outlier that might just hold clues to the origins of the outer solar system, and the conditions for life beyond Earth. Neptune has at least 14 confirmed moons. Most of them are small, irregular objects that orbit far from the planet, but Triton dominates them all. Discovered just 17 days after Neptune itself in 1846, Triton is nearly as large as Earth's moon, and larger than Pluto. Its surface is reflective, smooth in places, and covered in frozen nitrogen and other ices. And unlike any other large moon in the solar system, Triton orbits its planet in the opposite direction of Neptune's rotation, a retrograde orbit. This retrograde motion is a cosmic red flag. It tells us that Triton wasn't born alongside Neptune, like Earth's moon or Jupiter's Galilean satellites. Instead, Triton was likely a wanderer, possibly a dwarf planet from the Kuiper Belt, much like Pluto, that was captured by Neptune's gravity long ago. This capture event may have disrupted Neptune's original moon system, either ejecting earlier moons or causing them to collide. It was a violent chapter in Neptune's past, and Triton became its lasting legacy. Triton's surface is a frozen canvas of diverse terrain. When Voyager 2 flew past in 1989, the only spacecraft to ever visit Triton, it saw vast plains, ridges, fissures, and a curious dimpled texture known as cantaloupe terrain. Some regions are smooth and relatively crater-free, suggesting recent resurfacing, while others are etched with icy scars from ancient geological processes. Voyager also spotted dark streaks on the surface, evidence of geysers, erupting not with molten rock, but with nitrogen gas and icy particles. These geysers rise as much as 8 kilometers into the thin atmosphere and leave behind trails of dark material. The source of this activity is likely the sun itself, which slightly warms the frozen surface and triggers pressure buildups beneath a translucent icy layer. When the pressure becomes too great, the gas bursts through, carrying dust with it. This cryovolcanism is unlike anything on Earth, and it demonstrates that even at the edge of the solar system, geological processes can still shape a world. What lies beneath Triton's surface is even more tantalizing. Scientists suspect that Triton may harbor a subsurface ocean, a layer of liquid water mixed with ammonia, kept warm by internal heat and perhaps residual tidal forces. The evidence is indirect: resurfaced terrain, internal activity, and the presence of volatile ices. But if confirmed, Triton would join the growing list of ocean worlds that could, in theory, provide the right conditions for life. Triton also has a thin atmosphere composed mostly of nitrogen with a trace of methane. This atmosphere is cold, just 38 Kelvin or about minus 235 degrees Celsius, but it's dynamic. It forms hazy layers and faint clouds, and it may vary in thickness depending on the seasons, which on Triton last more than a century each. The presence of an atmosphere, no matter how thin, adds to the moon's complexity and makes it a prime target for future exploration. While Triton steals the spotlight, Neptune's other moons have stories of their own. Most are irregularly shaped and orbit at great distances. These small moons, like Nereid, Halimede, and Laomedea, are probably captured Kuiper belt objects, similar to Triton, but on a much smaller scale. Their orbits are eccentric, tilted, and in some cases retrograde, reflecting a history of gravitational disturbances. Nereid, the third largest moon of Neptune, has an especially eccentric orbit, so elongated that its distance from Neptune varies dramatically over the course of its orbit. This unusual path suggests it may have once been much closer to Neptune, perhaps displaced by the arrival of Triton. Other small moons like Sao, Samathe, and Neso orbit even farther out, some over 100 times farther from Neptune than Triton. These distant satellites are fragile, loosely held, and likely shaped by the outer edges of the planet's gravitational influence. Closer to Neptune, a handful of small inner moons circle the planet within the region of its faint ring system. These include Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus. They're irregularly shaped, likely composed of rock and ice, and their orbits are closely packed and almost perfectly circular. These moons may be the remnants of earlier satellites that were broken apart and reaccreted, or they may have formed from debris left over after Triton's capture. Proteus is the largest of these inner moons, and one of the darkest objects in the solar system. It's non-spherical, heavily cratered, and only barely large enough to have become rounded by gravity. When Voyager 2 photographed it, Proteus appeared battered and unchanged, likely geologically inactive for billions of years. Galatea, meanwhile, plays a role in shaping Neptune's rings, helping to confine one of the narrow arcs within the Adam's ring. Like Saturn's shepherd moons, Galatea's gravity keeps the ring particles from dispersing. The rings of Neptune themselves are faint and fragmented. Unlike Saturn's bright, continuous bands, Neptune's rings are dark and clumpy, likely made of dust and radiation-darkened ice. They were discovered in the 1980s from Earth-based observations and confirmed by Voyager 2. The Adams ring, in particular, contains several bright arcs, dense segments that seem to resist spreading out. This is a mystery, as physics suggests such arcs should disperse quickly. The presence of Galatea nearby offers a partial explanation, but the details are still unclear. In many ways, Neptune's moon system reflects a history of disruption and capture. The planet's largest moon was once a separate body, brought into orbit by chance and violence. Its small moons are survivors, leftovers from a time of chaos. Its rings are faint echoes of collisions past. Together, they paint a picture of a system shaped not by gentle formation, but by dramatic change. Despite the richness of Neptune's moon system, our understanding is limited. Voyager 2's flyby lasted just a few days, and much of the data we have comes from Earth-based telescopes peering across billions of kilometers. New missions are urgently needed to study Triton up close, explore the outer moons, and finally uncover what lies beneath the icy surfaces of these distant worlds. The good news is that interest in Neptune and Triton is growing. Future mission concepts include orbiters and flybys that could revisit this mysterious system. A Triton lander, capable of sampling surface materials or measuring seismic activity, could revolutionize our understanding of captured moons and cryovolcanic processes. An orbiter could study Neptune's magnetosphere, rings, and atmospheric dynamics, providing insight into how giant planets evolve in the far reaches of a star system. In the search for life beyond Earth, Triton holds a special place. If it does contain a subsurface ocean, heated and mixed by past or present tidal forces, then it might also contain the chemistry needed for life. And if it does, it would mean that even distant captured moons, once wandering ice balls from the Kuiper Belt, can become habitable environments. Neptune's moons, especially Triton, challenge our understanding of how planetary systems form and change. They are frozen witnesses to ancient migrations, collisions, and captures. They remind us that in the quiet dark of the outer solar system, there are still places where the story of life might unfold. Next, we'll explore another of Neptune and Uranus's lesser-known wonders, their rings. Dark, narrow, mysterious, and unlike those of any other planet. In Part 6, we'll dive into the fragile, dusty rings that circle these icy giants and uncover the hidden structures that shape them. Part 6. The Rings of Uranus and Neptune. Dark, narrow, and mysterious. When we think of planetary rings, our minds instantly go to Saturn's brilliant, wide, icy loops, the showpiece of the solar system. But Saturn is not the only planet with rings. All four of the giant planets, Jupiter, Saturn, Uranus, and Neptune, have ring systems. And while the rings of Uranus and Neptune may not shine with the same intensity, they are fascinating in their own right. Dark, narrow, and faint, they are some of the most enigmatic structures in the outer solar system. In this lecture, we explore the rings of the ice giants, how they were discovered, what they're made of, and the strange hidden forces that shape them. Let's start with Uranus. Its rings were discovered not by a spacecraft, but from the ground, and almost by accident. In 1977, astronomers were observing Uranus as it passed in front of a distant star, a technique known as stellar occultation. They expected to see the star wink out as Uranus moved in front of it. But to their surprise, the star flickered several times, both before and after Uranus passed by. The cause? Something was briefly blocking the starlight, something narrow and sharp. It was the first indirect glimpse of Uranus's ring system. Voyager 2 confirmed the rings when it flew past Uranus in 1986, capturing images of the planet's narrow, dark loops. These rings are not broad and continuous like Saturn's. Instead, they are thin, concentrated arcs, more like strands of thread than bands of light. There are 13 known rings around Uranus. Most of the material in these rings is confined to just a few dense, distinct bands, separated by large gaps. The brightest and most prominent is the Epsilon ring. This ring is just a few kilometers wide, yet it's densely packed and sharply defined. How can such narrow rings remain so stable? The answer lies in the influence of nearby moons. Tiny shepherd moons, such as Cordelia and Ophelia, orbit just inside and outside of the Epsilon ring. Their gravity helps corral the ring particles, keeping them confined and preventing them from spreading out. The other rings are fainter and less regular. Some are made up of smaller particles. Others are slightly wider or more diffuse. All of them are surprisingly dark, reflecting only a small fraction of the sunlight that hits them. Unlike Saturn's icy, shiny rings, Uranus's rings may be made of radiation-darkened material, perhaps icy particles coated with organic compounds, or dust from ancient collisions. The structure of Uranus's rings suggests a violent history. They may be the remnants of shattered moons, pulverized by impacts long ago. Alternatively, they could have formed from the debris of a catastrophic collision involving moons or passing objects. Whatever their origin, they appear young on cosmic timescales, perhaps just a few 100 million years old. Over time, micrometeoroid impacts and solar radiation may continue to grind them down, eventually dispersing them into space. Now let's travel even farther from the Sun, to Neptune. Its rings were harder to detect and weren't confirmed until Voyager 2 arrived in 1989. Before that, astronomers using similar occultation techniques had noticed irregular dimming events near Neptune, but the data were inconclusive. Some suspected partial rings, arcs that didn't go all the way around the planet. It wasn't until Voyager's flyby that the mystery was resolved. Neptune's rings, like those of Uranus, are faint and narrow. They're composed mostly of microscopic dust and small chunks of dark material. Voyager detected 5 main rings: Gale, Leverrier, Lassell, Arago, and Adams. The outermost ring, Adams, is the most famous because it contains several bright arcs, dense clumps of particles concentrated in specific regions rather than forming a smooth ring. These arcs defy simple explanation. Normally, particles in a ring should spread out over time due to orbital motion and collisions. So why don't Neptune's arcs disperse? One likely reason is the influence of nearby moons. The small moon Galatea orbits just inside the Adams ring and may act as a shepherd, its gravity stabilizing the arcs and keeping them from drifting apart. But the precise mechanisms are still not fully understood, and the arcs remain one of Neptune's enduring puzzles. Like those of Uranus, Neptune's rings are extremely dark, reflecting less than 10% of the sunlight they receive. They likely contain radiation-processed material, perhaps ice-coated in carbon-rich compounds, or the remnants of ancient impacts. These dark compositions are consistent with other features of the outer solar system, where high-energy radiation from space gradually alters the surfaces of exposed materials. The rings of Neptune may also be dynamic and changing. Observations since Voyager's time suggest that some of the arcs have shifted or faded, though the data is limited. Future missions to Neptune could help resolve whether these changes are real and what they mean for the ring system's stability. In both Uranus and Neptune's cases, the ring systems appear closely tied to the presence of nearby moons. The gravitational relationships between rings and moons are complex and delicate, creating a balance of forces that sculpts the ring's shape and behavior. This intricate choreography is seen at Saturn as well, but it's more subtle and hidden in the ice giant systems, where the rings are thinner, dimmer, and more fragile. The very existence of rings around all four gas and ice giants raises interesting questions. Are rings a natural stage in the life cycle of planetary systems? Do they form early and gradually fade, or are they the result of more recent cataclysmic events? Could new rings form again in the future if a moon is shattered or captured? These questions remain open, and ice giant rings, because of their unusual features, may hold some of the answers. Today, we study these distant rings from Earth-based observatories, often using infrared or stellar occultation techniques to track their structure. Space telescopes like Hubble and JWST can help as well, but the faintness of these rings and their distance from Earth make detailed studies very difficult. The next leap forward will require returning to these planets with dedicated missions. A Uranus orbiter, for example, could monitor the rings over time, observe how the shepherd moons interact with them, and detect new, smaller moons hidden within the gaps. A Neptune mission could revisit the Atom's ring arcs, solve the mystery of their persistence, and determine whether the rings are evolving or fading. These rings may not be showy, but their secrets are profound, and solving them could offer insights into the formation and evolution of planetary systems throughout the galaxy. In the grand scheme, the rings of Uranus and Neptune remind us that beauty in the cosmos comes in many forms. Not all wonders are bright or easy to see. Some lie in the shadows, quiet and mysterious, waiting for us to look a little closer. In our final lecture, we'll pull all of this together, looking at the history of spacecraft exploration at Uranus and Neptune, and what the future may hold. From Voyager's daring flybys to the next generation of orbiters and probes, we'll examine what we've learned, what we've missed, and what discoveries still await among the ice giants. Part 7. Exploration and future missions to Uranus and Neptune. Of all the planets in our solar system, Uranus and Neptune remain the most mysterious, not because they are unworthy of attention, but because we've barely visited them. Despite being rich in scientific intrigue, dynamic in behavior, and central to our understanding of planetary systems, these distant ice giants have received just one brief visit from a spacecraft. That spacecraft was Voyager 2. And its encounters with Uranus in 1986 and Neptune in 1989 were flybys, not long-term studies. In this final lecture, we look back at what we've learned from past exploration, what we've had to learn from afar, and what the future may finally bring as interest in the ice giant surges forward. Voyager 2's journey to Uranus and Neptune was part of a grand tour, a rare planetary alignment that allowed the spacecraft to use gravitational assists to slingshot from one planet to the next. The mission was a marvel of engineering and timing. When it reached Uranus in 1986, Voyager 2 provided humanity's first and only close-up look at the tilted giant. It revealed a pale, featureless world with a sideways rotation, faint rings, and a suite of moons, some smooth, others fractured. It measured Uranus's magnetic field and found it oddly tilted and offset from the planet's center. 3 years later, in 1989, Voyager 2 arrived at Neptune. It found a dynamic blue planet with fierce winds, massive storm systems, and the strange backward orbiting moon Triton. It discovered geysers erupting from Triton's surface and measured Neptune's own lopsided magnetic field. These encounters were brief, mere days compared to the years of orbiting missions at Jupiter and Saturn. But they changed our understanding forever. and left us wanting more. In the 3.5 decades since Voyager's flybys, we've learned what we can from Earth. Powerful telescopes like Hubble and Keck have observed cloud patterns and changing storms on Neptune. Infrared observations have hinted at temperature distributions and seasonal changes on Uranus. We've tracked faint moons and ring arcs, and we've used stellar occultations to study the structure of ring systems. But these observations, though valuable, are limited. From nearly 3 billion kilometers away, there's only so much we can see. And yet, our curiosity about Uranus and Neptune has only grown. These two planets represent an entire class of world, ice giants, that are common in our galaxy. Many of the exoplanets we've discovered orbiting other stars are similar in size and composition to Uranus and Neptune. If we want to understand what those distant worlds are like, whether they have atmospheres, storms, oceans, or even moons, we need to understand our own ice giants first. So why haven't we returned? The answer is partly technical, partly budgetary. Missions to Uranus or Neptune require enormous travel times, often 10 to 15 years just to get there, and highly efficient propulsion systems. These missions are expensive and require long planning horizons. For many years, attention and funding were focused on closer targets like Mars, the Moon, and the inner planets, or on Jupiter and Saturn, which offered more accessible science within shorter mission timelines. But that's changing. In 2022, NASA's Decadal Survey, the roadmap that sets scientific priorities for the next decade, identified a Uranus orbiter and probe mission as the highest priority flagship mission for planetary science after Mars sample return. This mission would be the first dedicated spacecraft to orbit Uranus and study it in detail. It would carry a suite of instruments to measure the atmosphere, magnetic field, rings, moons, and internal structure of the planet. A separate probe would descend into the atmosphere, sampling its composition and structure as it falls. Such a mission would be revolutionary. It could finally answer questions that have lingered for decades. Why is Uranus so cold? Why is its magnetic field so unusual? Do its moons have subsurface oceans? What are the rings made of? How did the planet end up tilted sideways? And how do all these systems interact over time? Launching such a mission would likely involve using gravity assist from Jupiter or Saturn, adding complexity but also increasing efficiency. Launch windows aligned with planetary positions are rare, so the next opportunities, particularly in the early 2030s, are crucial. If launched then, the spacecraft could arrive at Uranus by the mid to late 2040s. Yes, the timeline is long, but the science payoff would be immense. There are also proposals to revisit Neptune. Although not prioritized as highly as Uranus, Neptune holds its own set of mysteries. Triton, with its retrograde orbit and possible subsurface ocean, is a compelling target for astrobiology. A Neptune orbiter and Triton lander mission could answer major questions about moon capture, cryovolcanism, and ocean worlds. Concepts like this exist on paper but await funding and endorsement. There are also ideas for faster, smaller-scale missions. Flyby spacecraft could revisit both planets, capturing updated imagery and data. CubeSats or piggyback missions could accompany larger spacecraft. And as new propulsion technologies develop, like nuclear electric propulsion or solar sail boosters, the possibilities for reaching the ice giants more efficiently will expand. Even as we wait for new missions, new data continues to arrive. The James Webb Space Telescope, JWST, launched in late 2021, is already providing infrared observations of Uranus and Neptune that surpass anything previously achieved from Earth. Webb can detect cloud layers, temperature variations, and trace gases in the atmospheres of both planets. These observations are sharpening our understanding and laying the groundwork for future missions by identifying key questions and target features. And then there's the excitement of the unknown. Every mission to a new planetary system has brought surprises. Cassini revealed Enceladus's geysers and Titan's lakes. Juno is uncovering Jupiter's deep atmospheric bands and strange core. What might we find when we spend real time with Uranus and Neptune? New moons? Hidden ring structures? Geological activity on moons we've barely seen? Signs of habitability in unexpected places? In the search for life beyond Earth, the ice giants may seem unlikely candidates. They are cold, distant, and dark. But their moons, Ariel, Titania, Oberon, and especially Triton, could harbor subsurface oceans. If there is one lesson the solar system has taught us again and again, it's that life finds a way in the most surprising environments. A hidden ocean beneath kilometers of ice, warmed by internal heat, might be as promising as any Mars crater or Europa trench. In the end, exploring Uranus and Neptune is not just about filling in a blank on a planetary map. It's about completing the story of how our solar system formed, how planetary systems evolve, and how diverse and surprising planets can be. The ice giants are the final frontier among the major planets, a region we've only glimpsed, but never truly visited. The next chapters of exploration will bring us there at last. So as we conclude this series, we leave you not with answers, but with invitations to wonder, to explore, to discover. The solar system is still full of mysteries, and the ice giants, tilted, stormy, silent, and blue, are waiting in the dark, ready to reveal them.